OK, bonjour. Merci d'être venu. Donc, welcome. Thank you for coming. So, today is probably going to be, as far as algebra is concerned, I think this is the top. I mean, we won't do anything more complicated than that as far as algebra is concerned. So you have to watch me because I probably make lots of mistakes. So if I summarize what we did last time, well, first of all, you have to remember that, so if I represent the Green's function by a line, okay, that goes, let's say if I have G1, 2, I represent it by a line that goes from 1 to 2. Okay, I could go from 2 to 1 from the creation to the annihilation operator, and in the literature you find both conventions. Okay, so it doesn't matter. So we go from 1 to 2. Then that Green function is equal to the bare one plus the bare times the self-energy times the same Green function. So let me show you this a little bit. So you remember that if we add a general Green function, then we add the G0 minus 1 minus the self-energy times G equals 1, right? So that basically, and G0 minus 1, an example is I omega n plus mu, Km, I called it, plus mu minus epsilon k. That's an example. So G minus 1 is this, right? So this I can rewrite differently. I can write that G0 minus 1 is equal to 1 plus sigma times G, I'm sorry. G0 minus 1 times G. Is equal to 1 plus sigma G. So that G is G0 plus G0 sigma G. So in that form, it's often called, this is all the same equation. But often you see it in this form. That's called the Dyson equation. So you see you have G equals G0 plus G0 sigma G, okay? And these are all like matrix multiplications. So what is the self-energy? Okay, the self-energy, we saw that it is proportional to the interaction times a 4-point function times something that looks like psi diagonal psi diagonal. So another way to write it is like this. So these diagrams, you can look at them top, bottom, or left, right, or right, left. It doesn't matter. Okay. So here, sigma, I write this way. So the self-energy has an interaction here that I represent by this line here. Okay, and can interact with the mean field. We will see. This is like the Green function at the same time and the same point. So that's the density. So it's sort of a mean field R3 approximation. And this term is the exchange, which takes care of the Pauli principle. So, and also the fact that the particle doesn't interact with itself. Now, that's not the only way you can interact with the environment. So here is the interaction. So you have to think of a particle coming. That this is coming here and leaving there. Okay, so this is sigma 1, 3. I will show you all of this. I'm just trying to give you some intuitive notions of what we're doing. Sigma 1, 2. Okay, so you come here, you leave there. So what happened is that you interact, and you remember that it came from the potential energy. So there was upside, upside. So I'm interacting with the density here, and so these density fluctuations can be represented like this. So let me go back to this now. So this here triangle, which ends up with 2, is the same as 3, 4 with the same point here. Okay, so what happens? No, so if I have sent a particle and a hole, okay, the arrows don't go in the same direction, and you will see when I write explicitly the expression, but it's really like if I had the particle and a hole. I mean, this one can be the particle, this one can be the hole, and vice versa. But well, all that counts is that they're not in the same direction. So if I launch a particle 1 and a hole 2 at point 2, and I take them out at point 3 and 4, what can happen? I mean, they can propagate alone, but they can also interact with themselves and with everything else. So this is this box here. So more explicitly, what happens is that, okay, there's in quantum mechanics, you have to sum over all possible states, things that can happen in the intermediate states. Okay, so we know the initial state, we know the final state, and one of the peculiarities of quantum mechanics is that to go from initial to final state, you go through all possible paths at the same time. You lose the notion of trajectory. So 1 goes to 3 and 2 goes to 4 without doing anything. So that's one possibility. The other possibility is that it interacts here. Okay, so 5 bar, 6 bar means that it's integrated over coordinates 5, 6, 7, 8, and then it comes out with 3, 4. So this box here is what we call the irreducible vertex. So this was delta sigma delta G. So if we take sigma and we functionally differentiate with respect to the Green's function, you see the first terms that come in are just the bare interaction. So this is like the bare interaction plus everything we will get by taking functional derivatives of this. But the point is that in this box, we never have 2 lines that go alone like that. And so if you look at this, okay, there are 2 lines that go there, but if I cut these 2 lines, this piece is still attached to this one. But here I can cut the diagram in 2 pieces just by cutting this, okay? So if you look at this piece is repeated here. So it's the same as what happened there in this case. So in the sense, this is like a self-energy. It's called an irreducible vertex in particle hole channel in this jargon. But it's like the self-energy for this density response now, or if you want this 4-point function. Okay. So if I iterate this equation, in other words, the same way, if I add the, whoops, G equals G0 plus G0 sigma G, then this is, I can iterate. So it's G0 plus G0 sigma G0 plus G0 sigma G0 sigma G0 plus, etc. Okay. So I can hit this sigma many times. So the self energy that comes here, it's called the one particle irreducible. In other words, if I look at all these terms here, if I represent G0 by a line, sigma G0, sigma G0. You see that I can cut this diagram in two by cutting one line. But the sigma itself, if I cut one line, I cannot split in two. So it's called one particle irreducible. I mean, I know it's a lot of jargon. I will come back to all of this very slowly, but I'm sort of giving you the insights. So here it's the same way. I mean, if I iterate now, what I will get is something like this. I will get this, then the box, this, then plus this, the box, red box, this red box again, this, okay. So I can cut the diagram in two like this. What goes inside here is a particle all irreducible. I cannot cut it in two pieces by cutting these two lines. Okay, so much for all this jargon. Why are these important? These are all exact equations, but all the approximations that we will do from now on, I think at least most of the approximations, are just based on approximations of these equations. So the random phase approximation, what will happen is that this red box we will replace just by the bare interaction. That will be the random phase approximation. Then when we go to the GW approximation, that's very famous in the context of electronic structure, all that we will do is to use this expression for the self-energy, but with this red box, again, replaced by the bare interaction. So it's like putting RPA here. And then we will also see the two-particle self-consistent approach, where we will approximate the box here using, for the Hubbard model, using some rules, so that it's not perturbative, okay? But you have basically, I could say that the most important parts of many-body physics, or at least some of the most important parts, are in these equations that I will now derive algebraically and make a lot of mistakes, okay? But you will see what all these objects mean. Okay, you have any questions? Okay, so I will proceed just like we did for the three-particle case, in the sense that I will first write down the Hamiltonian, then compute the derivative of the psi1 with respect to tau1, and then given this, I will be able to write the equations of motion for G. Okay, and writing the equations of motion for G, the d tau is like G0 minus 1, is a part of G0 minus 1 when it's expressed in time. And this thing will give me an expression for sigma. So it will tell me how sigma is related to these fluctuations. And then in sigma, there is a psi dagger psi that comes in. So I will relate this to delta G, delta phi. So this equation here will contain phi, and I will be able to take this functional derivative. And then, okay, given how I can get this 4-point function from this, I will compute sigma given what I have learned here. Okay, so in other words, I will first focus on this, and then I will be able to write the equation for sigma. And this I already did. I mean, I already discussed this notion of irreducibility, but I can come back to that. So is the plan okay? Okay. So what is the Hamiltonian? So we have H0, so for this Coulomb gas, but you realize I will write H0 for the Coulomb gas, but basically it will be very easy to, there's no more calculation to do for any H0 and any interaction here. Okay, I will do for Coulomb, But the generalization, you don't need to do anything more. All these diagrams are still the same. It's just that the line mean different things. They mean a different interaction. They mean a different G0. But if we do it with this, then we have it in general. So H0 was equal to minus sum over spins of integral dx. I will not write d cube and put vectors and so on, but you can think of this as a 3-dimension. So psi dagger x sigma, there's a minus, okay, so grad square over 2m psi sigma x, okay. So that's some H0 is a little bit like that. In fact, I need a K0. I mean, I need I need to put the chemical potential there. So K0. So that will be minus mu sum over sigma of integral dx psi dagger x sigma psi sigma x. Okay. Okay, and then we have the interaction. Okay, so the interaction, the piece that is the interaction. So let me call it V as an operator. Is equal to 1/2. Can you see that? Yes. Sum over sigma 1 sigma 2 of integral dx1 integral dx2 of v of x1 minus x2 times psi dagger sigma 2 x2 psi dagger sigma 1 x1 psi sigma 1 x1. Wow, it's quite dangerous. We're getting to the end here. Psi x2 sigma 2. Okay. Okay. And now there's another term that is just the background. The background. So what happens with the background is that we replace let's say this density, for example, we replace just by some constant density that doesn't depend on x1, doesn't depend on sigma 1. That's the background. So we will see when we do calculation that just amounts to removing q equals 0 quantity. So everything that is uniform would cause divergence if we didn't have it, but because we don't have a q equals 0 contribution, everything will be well behaved. I won't write it because it's a little bit a waste of time. Okay, so v of x1 x minus x2 for the Coulomb gas that we are doing now is just e square over 4 pi epsilon 0 times absolute value of x1 minus x2. Okay, but we don't need this. We will need this explicit form when we do calculations, but we don't need it now. So is that okay for the Hamiltonian? Okay. So now to find the equation for this, I need to know d psi 1 d tau 1. So d psi 1 d tau 1 is equal to, so we remember the equations of motion for psi. You add e to the k tau, e to the minus k tau, so it's equal to the commutator of the k with the psi 1, where k is k0 plus v. Okay, so there's an easy piece, which is this one here. So what happens with this one is that this is basically like the number operator, and the number operator with psi1 gives you minus psi1. And you were in the homework, you've worked on these similar commutation relations. So there's the piece that comes from this is just equal to rad square over 2m plus mu times psi1. Okay, that piece was not too difficult. But now we need to find the commutator of this. So that's a little bit more of a mess. And I'll give you the answer and we will see why it's that. So the answer is that it is equal to minus sum over sigma 2 of integral dx2 of v of x1 minus x2 times psi dagger sigma 2 x2. My pen have problems. Times psi sigma 2 x2 times psi sigma 1 x1. Okay, why is that? Well, you see, the important piece is the commutator of this with psi1. So let's write it. So I have psi dagger sigma 2 x2 psi dagger sigma 1 x1 commutator with the psi of x and sigma. There's no 1 here. Psi sigma x. It will become 1 in a second. Psi of x. And here I have psi sigma 1 of x1 psi of sigma 2 times x2. Okay, so remember that the commutator of something like that, so it's, if you want, I work with a, b, c is equal to a, b, c plus a, c times b. And for a, I took this piece, and for b, I took this piece. So since I know that destruction operators commute with themselves, I didn't write that piece. So that's the only thing that's left, okay? Now you see there will clearly be 2 terms, and that's what will get rid of the factor of 2. The factor of 2 takes care of the fact that you count interactions twice, but then when you look at just one particle, it interacts with just once. So if I compute this with respect to x1, so I get the, so let me focus on this now. I get the psi dagger of sigma 2 times the anti-commutator of psi of sigma 1 dagger x1 psi sigma x minus psi dagger sigma 2 of x2 times the psi sigma of x times the psi dagger of sigma 1 x1. Okay, so now I'm using the rule for the anti-commutators. So this is delta of x minus x1, delta sigma 1. And this one is just delta of x minus x2 sigma sigma 2. Okay, so if you take this, which piece now? If I take, I hope I didn't make a mistake. If you take this, so I want to arrive to this. Okay, so let me take this piece. Then there's delta sigma sigma 1. So I have sigma 1 has become sigma here. And I have the sigma 2 that is here. So it means that and here the sigma 2 was here. So I needed to exchange these two guys, right, to put it in that form. So that explains the minus sign here. And then in the other case, sigma sigma 2. So sigma is equal to sigma 2, but I have to just change the label 1 for 2, and then everything works out. Okay. So assuming I didn't do any mistakes, I think this is the right answer.
Just to be sure, is there any reason why the small v for the potential at a given point is not dependent on sigma 1 and sigma 2?
In general, we should put it dependent on, I have to put the x here. In general, there should be some spin dependence, but here it is the Coulomb interaction, so there's no spin dependence. You have to be careful that it cannot flip the spin. So if you come in with a certain spin, you have to leave with the same spin. Okay.
You're right. Thank you.
So yeah, that's why here, for, wherever we see we come at point 2, and we come and we leave at point 2, and we leave with the same spin. For a general potential, it could be that the spin here is not the same as the one here. So it can flip spin. But here with the the Coulomb interaction does not flip the spins. Okay, so now I can use this to write the equation of motion for G. Okay, why? Because now if I do d tau 1 of G of 1, 2, okay. There's a term that is equal to minus delta 1 minus 2. Remember what? Why? Because when the d tau 1 acts on the theta function that comes in the definition of the time-ordered product, get the derivative of the theta function, and there's an overall minus sign here in front of this. And you get the anti-commutator, and that gives not only a delta function in time, but also a delta function in space. And all the other indices, space and spin. Okay, so that's the first term. Now there's the d tau 1 acts also on psi1. That's why we are in this, but that's why we worked out this. Otherwise, it was a waste of time. So, so now, because of the minus sign, we get. Let's see, did I get this correctly? The psi1, so there's a psi1 will be there. So we get plus grad square over 2m plus mu times g times g of, so this is coordinate 1, g12. And then we have this mess here. So that will be, let me write this as minus v of 1 minus 2 bar times let's see, there's a deep psi1, there's a minus sign here, but there's a minus sign there as well, so I think it's
it should be a plus.
It should be a
I'm
plus.
pretty sure.
Right? This is here that I made a mistake then, because I think this is really a minus here. So I have psi dagger 2 bar, psi 2 bar, and I have this psi here, psi that was at the coordinate 1, so psi 1, and then the g, in the g there's a psi dagger 2, right? So the g is defined, let me remind you that the g is equal to g of 1, 2 is equal to minus the time ordered product of psi 1, psi dagger 2. So now I'm computing the time derivative of this, but the psi dagger 2 I just put here, right? So psi dagger 2. So I know this is right, so there must be a plus sign here. Nobody saw the mistake?
I just check in your note, and there's the sign on the above equation is right.
So what happened to this one then?
In the note,
We had, go ahead.
yeah, in the note it's a plus sign.
It's a plus sign? Okay.
Mm-hmm.
Oh, yes. Okay, I know why. Okay, very good. Thank you. Okay, so we didn't do a mistake. I just, it's here that I didn't remember correctly. Okay. So something has happened here. And what has happened is that I have introduced some time dependence in the potential here. So if you want, V of 1, 2 is equal to little v of x1 minus x2 times delta of tau1 minus tau2. Okay, so when I integrate over the 2 here, I integrate also over imaginary time. But there's no time dependence in this v. So I need to put tau1 equals tau2. Okay? So that's a nice shorthand notation. Okay. Now there's one more term. Because we want to work, you remember, with something that is that still depends on this source field phi. So I need to take the time derivative, not only of this field operator, the psi1, but I also need to take the time derivative of the contribution from the source field. Okay, so let's, and the result will be that here we will get plus you have to add me now. I don't remember if it's plus or minus. You get plus of phi 1 2 bar G of 2 bar 2.
In the note, it's a minus sign.
The minus, huh? Yeah. Okay, thank you. Okay, let's do the calculation and see if the minus works out. So I need to compute d theta 1 of the time order product of exponential of minus integral from tau 1. I will put the time order, the correct time order, from tau 1 to beta d tau 1 prime integral d cube x 1 times psi dagger. I'll tell you why I'm doing this in a second. Psi dagger of x1 tau prime 1 times phi of x1 tau prime 1 times 2 bar psi of 2 bar, and now I have psi 1 here, and I have e to the minus integral from 0 to tau 1 of d tau prime 1 d cube x1, same thing, psi dagger of x1 tau prime 1 phi of x1 tau prime 1 2 bar psi of 2 bar and psi dagger 2. Okay, so you see what I have done is that it's only the psi dagger that doesn't commute with the psi. Okay, so I've split the tau integral of the psi dagger into two pieces, the piece where the tau prime 1 is larger than the 1, and the piece where tau prime 1 is less than tau 1. Okay, so I put them in the right time order. Okay, so now when I differentiate, what will happen? What will happen is that I don't have any more space to work. So what will happen is that I get dt, here dt tau 1, I mean, the derivative, an integral is just the argument, okay, evaluated at tau 1. But here it's the lower, I mean, it's the lower bound, so I get a plus, okay? And so I will get t, the time ordered operator of, okay, this piece here, this whole thing I will call A, just, okay, yeah, to save space. So this whole thing is A. And now when I differentiate the exponential, I have the integral d cube x1 psi dagger of x1 tau 1 phi of x 1 tau 1 2 bar psi. Oh my God, all my pen are abandoning me. Psi of 2 bar. And now this is commuted with psi 1. Because when I take the derivative to the left, I get this, and to the right, now I have the upper bound, so I get a minus sign. So psi 1, and now this whole piece here, I call B, and I have psi dagger 2.
Ouais, ça commence à être difficile à lire
Ouais, hein?
les feutres.
Je vais changer pour le bleu. Okay. But now we know how to do the commutation for this. So it will give me so that when it's the anti-commutator and I need to move this to the left, it's as if I was, the way to remember it is as if I was anti-commuting with this. So I will get an extra minus sign, and I will get a delta function of this guy equals to this. Okay. So that's why I have phi 1 here. And then the 2 bar, the 2 bar is this field is still there also. So I have 2 bar here, which is this 2 bar, and I have 2 bar here, which is this 2 bar, and I have 2, which is this 2. Okay.
Small question.
Yes.
Should we have, when we applied the derivative, we made sure to apply the derivative on both exponential, but there's a psi 1 in between of them? Shouldn't we have a contribution from this term?
We do, but we took it into account already here.
Oh, okay.
Mm-hmm.
Yeah, all right.
So this beta 1 we took into account here. So good question. So, but now we're working on this. Okay. Okay, and now I lost track of the minus signs, but okay, there's a minus sign that comes in the definition of G. So probably there was a minus sign here already, and that's why I have a minus sign. Okay. Oof. Okay. So that's the most messy part of the derivation, if you want. assuming that we have done it correctly. Then you see what we can do. That's the important piece, is that I can write now the equation of motion for G. So I multiply by a minus sign here everywhere. So is this sign correct?
Yes.
Yes, yes.
Yes, okay. So I have a minus, I multiply everything by minus sign. So when I put it on the left, this becomes a plus. So plus grad square over 2m. Somehow it sounds wrong, but plus mu. And then we have this x. Then we have this. So we multiply by minus and put on the left. So that becomes plus. When I push to the left, it becomes minus. So minus phi. Okay, I forgot something here. So this whole thing here will act on delta of 1 minus 2 bar minus phi 1 2 bar and G of 2 bar 2. You see what happened? So the two bar here, this becomes a delta function that becomes 1, just like we had here. But now, because of this phi, it allows me to write this in a more general way. And now that's equal to, I multiply by a minus sign. So that's equal to delta of 1 minus 2 and minus V of 1 minus 2 bar times this mess here. Time ordered product. I forgot the time ordering operator here. Time ordered product of psi dagger of 2 bar psi. Okay, here, because of the time ordered product, I need to put a plus here. Okay, to specify that this is always to the left, because it came from V, remember? So in V, it was to the left. And in a time-ordered product, if I don't put this plus, it doesn't mean anything, okay? Because a time-ordered product needs to know what is to the left, what is to the right, because they don't anti-commute. They don't commute or anti-commute. So I have 2 bar plus, and then I have 2 bar here. So that's this. And then I have psi 1, and I have psi dagger 2. Okay. So what have I shown? And I'm going to stop here. I've done about half of what I should be doing, but it has to be done slowly if we don't want to make mistakes.
Why are there 1 indices? Because so in the notes you have G of 1 and 2 on the left and G of 2 bar and 2 on the right. G, I mean, when you write G and you have a, yeah, this expression. When in the notes there is, oh no, oh, okay.
The
So we
note
have
there, what?
No, I'm sorry, I got confused.
Okay. So, how does this look like? I mean, so you see, this is a definition now of G0 minus 1. So this expression is G0 minus 1 of 1, 2 bar minus phi of 1, 2 bar times G of 2 bar 2 is equal to delta 1 minus 2. Now plus sigma of 1, 2 bar G of 2 bar 2. Okay, that's Dyson equation. And we know that the Green's function has this form. So what happened now is that we have defined what is the sigma. Sigma is this times G minus 1. So next time we will given this expression for G phi, and that the nice thing here is that depends on phi. Given this expression of G of phi, I will be able from functional derivatives to generate this equation. And then given this equation that is, just representing 4 field operators, psi group psi, psi group psi, if I take delta G, delta phi, I get something like this. I will be able to use this expression to write the expression for sigma, and I'm done. Okay. So just to be clear, I have that sigma of 1, 3 is equal to minus V of 1 minus 2 bar times the time ordered product of psi dagger 2 bar plus psi of 2 bar psi 1 psi dagger now of let's say 4 times G minus 1 of 4 bar 3. Okay, so these are all matrix multiplication. So this was this was multiplying this index, this 2 bar. I'm not sure I got this correctly. I get the G minus 1 of 2, 3. I have to multiply by G minus 1 of, if I call this when I take, well, I should have written it explicitly. When I write this, for example, as 4, if I multiply by 4 bar 3, then it comes out this way. Okay, I think I wrote the wrong thing. Anyway, we should finish now. I think I will redo this next time. I mean, this is correct. This is correct. This, I think I made a mistake. Okay, so any question? Okay, so on Friday, we are a little bit late on the schedule, but I think it's worth doing slowly. So on Friday, we will start from the expression for sigma 2 here. Okay, sigma 2G is this. So I will write the equation here. Sigma 2G is equal to this. Then we will get this 4-point function from functional derivative, and then we will be ready to write sigma. Okay, and the nice thing is that, as I said, is that these equations are completely general. They don't rely on, I mean, this, I could put any G0 I wanted. And the interaction here, all that it needs to be a two-body interaction like this. I could have written something more general, like Olivier suggested, with the spin indices, but there we don't. There's enough complication like this. In fact, I should have written this. Yes. So remember the 1 and 2. These include the spin indices in this thing here. And we will use that eventually. Okay, any question? Okay, so I will stop recording.